Is anyone familiar with the technology here? Because 16. Yeah. Well, I mean.
Yeah, that's okay.
Hello. Yes. Can everybody hear me?
Only because your voice, the mic doesn't seem.
Hello.
Yeah, that's right.
A little closer. Yeah.
All right. How about this? Okay. So for the last few weeks, after I was told that I was going to actually do this presentation, I've been thinking quite a lot about how to present this in a way that will be interesting to. I mean, I have a very limited amount of time, and I have to try to explain to a group of people who has never, most of you have probably never seen this, and somehow I have to try to convey oh, that was my mother, by the way. It's true, it's true. If only my childhood would have been so much better. Anyway, so I'm desperately trying to come up with a way to explain why a programming language can be so good, and I have half an hour to do it, and because at the end of the day, all programming languages are the same, right? I mean, you write code, the computer does something, but so I started thinking about all the different things that makes this so much better than all the languages. Could be the object orientation, which is so much more expressive than any other language, but at the end of the day, most of these features exist in all the other languages. Even though they're not as good, there's no way for me to actually explain why. So I need to get at least a few of you to continue to pursue this subject and maybe read up a little bit more so that you will understand why this is so great. So, but if you were to ask a random Lisp programmer, name one thing that makes Lisp a very different language, that makes it better than everything else, and most of those people would probably mention macros. Now, so I decided to, okay, let's just focus on one feature. Let's focus on macros and see if I can sort of convey an idea of what macros are all about. Because if I just mention macros, most people who are familiar with C or C++ say, oh, well, you have hash define, and those are macros, and they suck, which they do. But this is different, and also not. But we'll get to that. So let's start with a little bit of history first, and let's go back in our minds to somewhere in the mid-50s, where programming was mostly done on punch cards, if you were lucky. If you had the latest technology, you would be using punch cards. And programming languages was mostly assembly, machine code, flip switches. And this is actually Fortran 77. So this is a couple of decades after the 50s. The 1950s version was even more terrible. But as you can see, the language itself, back when Fortran was the only programming language out there, at least that is still in use today, as you can see, the language is very, very similar to what comes out of the compiler. Right? So you assign a variable, a 0 to a variable. You write some text, you call the write function. You add 1 to a value, and that was what programming was all about. So then along came a guy called John McCarthy, and in 1959 he published a paper on symbolic programming, where he brought up a lot of features that did not. He came up with.
Oh, they didn't exist before that?
Exactly. So these are things that we use today in pretty much all languages. Conditional, so you have an if statement, right? Imagine a world where if statements were limited to if something, then go to. What was introduced with if statements was if, do something, and if, or else. That kind of structured programming didn't exist. Garbage collection, obviously, took decades. I mean, it wasn't really until Java in the 90s where garbage collection really became acceptable as a feature of programming language. But these days, I mean, pretty much every language out there, with very few exceptions, do the garbage collections. You have all the modern latest Ruby's and Pythons and all those things. And they're all garbage collected. It's natural these days, not to mention JavaScript. First-class functions is something that remarkably is considered fairly new even today. And many languages that do have them, programmers don't tend to take advantage of that feature. Now, okay, so I need to do a little bit of show at hand here. How many people immediately understand if I say first-class function, what that actually means? All right, we get a decent number of hands, that's good. So for the rest of you, first-class function is essentially you assign a function to a variable, and then you can carry that variable around and call that variable through, call the function through the variable. It's more than function pointers. Function pointers, as you see, is sort of halfway there, but you can also assign what's called an environment to the actual function pointer, which is called a closure, which is referred to as a closure. But that's sort of a little bit outside of today's code. Recursion didn't even exist. Recursion was something that was, well, it was unheard of. And the last one may require a little bit of an explanation. Everything is an expression. That is, an if statement is an expression that returns a value. If x, then y, else z. The value of the expression is either y or z, depending on the input value of x. And so you can assign, so you can do, assign the result of an expression, so you do, w equals if x, then y, else z. That kind of expressions. Even today, there are languages, JavaScript for example, that are fairly new, that still does not actually take this feature and run with it. They still have this arbitrary separation between statements and functions. Sorry, statements and expressions. So all of these things, and many more, were introduced already in 1959. But then it took decades for these features to become accepted, and it's not until now that we actually see these features in many other languages. So the first Lisp is a little bit of a, when I was researching this, there's a little bit of disagreement when the first Lisp actually came out. So they started work in 1955, Lisp 1.5, which was the first real version, came out in 1960. There was also Lisp 1 in 1959, which was sort of halfway. Anyway, so in 1960, it's a good date to use. And then you had many different implementations. You had specialized hardware. Many of you probably heard about the Lisp machines. And they were incompatible. There were a lot of issues. And so it was, standardization work was started in 1985, and then it was standardized as the ANSI standard Lisp, Common Lisp in 1994. And that's the baseline of all current Lisp development. on top of that, you have community development just like in any other non-standardized language. So for example, Common Lisp does not specify threading, how it works, but pretty much all of the actual implementations, there are about 7 of them, they do threading pretty much the same way, and there's a standardized language that everybody uses. So there is a very rich ecosystem around it. Now, a lot of you probably heard, oh, Lisp, that's that programming language with parentheses, right? And it's true, but yes, and that's what people say. However, if you actually count the number of parentheses, it's not much different from any other language. But the problem, or whatever you want to call it, is that Lisp uses parentheses for everything. So in some languages you have begin, end, or braces, or square brackets, or anything like that. Lisp uses parentheses for all of these. So that's why you end up with, when you in JavaScript, for example, end a function with end brace, end parentheses, 2 open parentheses, and then an end brace, that would be just like a list of 9 parentheses at the end of the expression of this. But at the end of the day, it's still approximately the same number. So what does Lisp code look like? Let's take a look. Hello world, very simple. This is actually not very different from JavaScript. The only difference here is that in Lisp, the parentheses go around the expression. So you have the function name first, and you have the parentheses on this side as opposed to this side. Other than that, there's no difference. And I will bring up examples as I move forward, and these examples will, in some cases, be somewhat complex because I need to use features that I haven't talked about. But that's beside the point, because usually I only want to illustrate one specific thing, so you just accept the rest. That's the way it is. If you're interested later, send me an email. I'll explain it further. So let's take a further example. Now, another thing that makes the language a little bit more rich in parentheses is that when, for example, in most languages, when you add 2 numbers, you do x plus y, you don't have infix operators in this. Right? So you have to have a function, and the function in this case is called plus. Lisp is much more free in terms of naming functions, so you can have a function called plus, or you can have a function called / / if you would like that. It's not limited to just words that most other languages have. So adding 2 numbers, you call the function plus and pass 2 parameters, 1 and 2, this were 3. So in JavaScript, this would be the way you would call the function plus. I mean, obviously it couldn't be called plus because JavaScript doesn't allow that, but let's call it add, and then you would call the function. So when you define a function, so I have to go through these basic things because I have some more complex examples later that illustrates. I will be moving into macros in a little bit, but you need to understand what the basic, simple function definitions of those things. You need to understand what those things look like for those other examples to make sense. So, define function, the name of the function, the parameter list, and format that's like printf in C. Actually, I put in the similar code in C just so you can compare. So format T is the same as printf in C. T there just means where the output goes. Then instead of percent sign, you have the tilde, so tilde A is the same as percent S, tilde percent is the same as \n. Other than that, it's pretty much identical. And if you count the number of parentheses, you will actually see that it's the same. So, Lisp means list processing. That's where the name comes from. So, let's just look. So, there are lists, and that's a fundamental data structure. And I could now spend a lot of time explaining what a cons is, and the fact that the Lisp objects are cons is essentially a pair of 2 objects, and they chain them together in a list, and then there are the dot notation. I don't know. Let's not talk about that. Let's just take a very simple example that illustrates just the key features that you have to understand right now. Right? And that is that this is a list of 4 elements. Right? Element 1 is a digit 1, a digit 2, a string, and then the 4th element being another list, in turn consists of 2 elements. So again, in order to sort of bring you to something that's familiar, most of you knows JavaScript, and the same list in JavaScript like this. Me, I find it very, very convenient not to have to do the commas in Lisp. It's just a space. And I find this to be much more readable than this. But that's just me. And I would think that most of you would think the same after being subjected to this stuff for more than about 45 minutes or something. So I'll bring up some examples. These are just functions that do stuff. So I have a function called Lisp that takes any number of arguments, and it will simply return a list with those arguments. So the return value of this is a list of what it is. There is a function called car, which returns the first element. There's another function called CDR, or color, that returns the rest. So color of this list would be 2, 3, 4. And there are some very historical reasons why those 2 functions are called car and color. And it has to do with the platform, the machine, the IBM 7. But it's a machine that was used to implement the first Lisp. They actually had 2 registers. It had a large register that had 2 parts, 3 actually. And so the address part and the decrement part, and the underlying implementation implemented that as they implemented the pair as 2 part of the same registers. And this means actually content of address register and content of decrement register portion. But Common Lisp actually gives you an alternative name, the name called first, and this one is called rest. And if you have, there is one popular variation of Lisp these days called closure that actually did away with these 2 names altogether, and you only have the names first and rest. But most Common Lisp programmers still use car and color. Probably, at least for me, is because it's shorter, and once you learn, you don't have to. It's not easier with those names. You have another function called mth, nth. So mth 2x would return 3. The nth would give you the nth value. To reverse the elements, you can sort, and you can append them. You have something called append. You have a huge number. I think it's on the order of 50 more of these that do things with the lists. But suffice it to say, you can do stuff with it. Yeah? The functions, again, I was a little bit, I was having a bit of a problem in writing this. I didn't really know if this slide would make any sense to most people. I put it in still because I did want to mention it, that you do have the same kind of functional features that you have in any other functional programming language. Your map car, for example, it will call this function on each element of the list. Now, the key here is that you can also have anonymous function called lambda functions, which, so in this particular case, you would take the list x, which contains 1, 2, 3, 4, then you would call this anonymous function on each element. So this function would add 10 to the value, so the return, then the return value of mapcar is a concatenation of all the values that came out of here, so the result is 1 to 11 over 14. Again, I mean, I don't expect you guys to remember this, and no one, but I want to sort of illustrate in a way just how what the language looks like when you're actually doing development. Now, so a little bit of a quiz, and this is interesting actually. So you saw this. a couple of slides back. So you might ask yourself, is this code that declares a function foo, takes one argument, and adds one to the argument? Yeah. Yeah, I guess. I mean, you can run this, and we'll do exactly that. It will define that function. But you can also ask yourself, is this a list? As you can see, the syntax is the same. Yeah? This could be a list of define, a foo, another list, and another list. Could be. So the answer is both. And this, if you're only taking away one thing from my talk, is that. That's the one thing to remember. That is the one thing that makes Lisp so different than all the others. So, if we have a variable x and it contains this list, so you can take the first element of that and it will give you the fun. You can take the rest and it will give you this. Or you can take the third element and we do another list. So why is this useful? Well, it is useful because it allows you to manipulate code as if it were data, because code is data. So what you're doing here is you're not, like in most other languages that have macro systems, you're not manipulating the strings, the text, the sequence of characters that represents the code. Instead, what you're doing is that you're manipulating the underlying data structure. It's just a tree structure, the parse tree essentially. And you're manipulating that in the binary form. So, getting the number 2, suppose that you get the fourth element of the list and then the second element of that list that returns is a 1, and that is the number 1 as when the code is running, not the text, the ASCII character 1 or Unicode character 1. It's actually the number 1 as stored in the underlying binary representation. And this allows you to do so much more than the traditional languages development. So in traditional languages, you start the source code, you have a text file or any, and they contain characters that represents the code. It goes through this black box, and out comes an executable that you can run. Usually, I mean, obviously, that's a little bit of a language, but in C, for example, C++, whatever, Java even, you take your source code, you compile it, and out comes the executable. You run the executable, and you have your program right there. Now, the purpose of the black box is to take the text that you write as a developer and create something that a computer can run. And but inside the black box, the compiler does more than one thing. It actually takes your input and then it tokenizes the code into a sequence of symbols. So it could be the symbol X, or it could be a string, or it could be a number, or it could be a list that in turn contains more symbols. But yeah, let's parse that. The tokenized step, it gives a symbol, so it could be an opening parentheses, and then comes another symbol, a 10, or another symbol, comma, whatever. Then the parser takes this and generates a tree structure that represents the code. So in JavaScript, for example, the top of the tree could be if. Right? And then it has 3 children, which is the expression, the then statement, and the else statement. And then further down the tree, the then statement could be another list of string, and then and then an expression or whatever. So the parsing creates this tree. And then the compiler takes that tree to create machine code that you can run. And then probably writes it to a binary file, and then you // and then you run. So what makes Common Lisp unique is that these steps are exposed to the load. You can do stuff, whatever you want, in here, or in here, or in there. So, for example, so we have something, okay, I'm going to try to explain what this is. Now, def macro is sort of like define. It defines a macro as opposed to defining a function. Let's call it if negative. Just the purpose is just to reverse the else and if the else and then statement. So it takes three parameters. Take the class, it takes the else statement, and followed by the then statement, because we want it reversed. And we return a list of if, then the class, then the then statement in the other way. So if you were to type this, if and t is true, so if true, then this. And what happens here is that when this code is read into your environment by the compiler, it will take this sequence, it will create the parse tree. So all the way to create the symbolic tree of the objects and whatever is inside the environment in the runtime. Then it will call this function with this data, gives it an opportunity to rewrite that content to generate this. And this is what's subsequently being compiled. So not only do you have the ability to change the syntax of the language, you also have the ability to do computations during compilation if you want. Now, you can do some of those things in C++. I've seen some grotesque things people do. People computing powers of Hanoi in C++ templates, which is a terrible idea, but it makes for a fast result because the generated binary will contain purely the output, the solution. The solution will actually be computed during compilation. But to do this, you have to jump through an enormous number of hoops because C++ is not designed to do this kind of magic. They sort of shoehorn it in and convince it to do things it wasn't designed to do. However, in Lisp, it's designed to do exactly that. So you can hook in and do your computations during compilation, and those can be anything you want. And you can go even further, which I will show you now. This, you don't really have to care what this technically, or exactly how this is implemented. Suffice it to say that this implements a new way of writing strings. So I could, normally a string is a double quote, a sequence of characters, another double quote. Here it's actually hash. I decided to make it hash opening brace, and then you could do some other computation and oh, this one is the wrong way. Never mind. The key here is that this is we're moving even further back. We're moving to the first step, the tokenization phase that I had in the slide before, that you can actually go in and tell the runtime or the compiler how to convert your sequence of letters into the parse tree that is then subsequently processed by the macro developer. So, for example, this feature is used there is something called CLSQL, which is one of the SQL client libraries for this. It actually allows you to put in raw SQL code within square brackets. And they did that just by adding your own new reader, called a reader macro. And so I know that some languages have this feature. I believe that Microsoft has an extension to C#, I think, where you can actually put in SQL code in the middle. I know that Oracle has a preprocessor for say, which basically takes your code, extracts the SQL, generates the code, and generates a new text output that is super complicated. However, they either need to design a new programming language or have a macro processor run before the actual compiler working on the text, which means that your macro processor in C would have to understand the full syntax of C, or maybe even C++, which is, I believe no human being on earth is actually able to fully understand the syntax of C++. Now, with Lisp, however, you do it in a handful of lines of code because it's integrated in the language itself. So you can do this processing without coming out with a new version of the language, without having a preprocessor, and without changing anything for anyone else. Because obviously the new reader will only be active if I choose for the files were activated, so there is no problem. So that's also one of the reasons why there has been no new language standard since 1989. That's because you don't really need to a lot of these extensions to the language has come as third-party libraries. You just load the library and you have the extension. Now, sorry. So, given what I've said now, questions maybe? Anyone? No?
Yeah, how do you get started on your design book, like interpreter or like just
I
get
have a
started?
couple of links actually that illustrates that a couple of slides forward. So, because if at least one or maybe two of you decide to look into this, I think I've been successful. Learning a new programming language, if you really have nothing that pushes you to do it, is hard, and a lot of people don't want to get be bothered. But I do suggest people to actually do bother a little bit with it, because it's kind of eye-opening in a way.
So you're saying that you just prepend this to the code that uses
Yeah, usually what libraries that do this, for example, the CLSQL library that extends the syntax, what they do is they give you a macro call and they say call this, and then because as the parser reads the file, the macros will be executed, so your macro will run before the rest of the file are parsed. So if you modify the reader inside a macro, then the new reader definition will take place for anything that is read below there. So all you do, they tell you basically, yeah, put this call, put it first in the file, and then from there on. So they wrap it in a macro. So it's for CLSQL, I think it's CLSQL colon enable SQL reader syntax. It's an enable macro. You just put that first in the file, and boom, you have your new syntax. So you could, for example, there is a way. If you install something called infix, standard library, you just install it. And infix will actually give you operators. You can type 1 + 2 - 3. And they do that through a reader. Most people don't use that because once you learn the Lisp way, you don't really feel like it. So, but it's normally used by people who do a lot of maths in Lisp. Then they use the infix library, and all of that, suddenly you put #I and then any expression, and the reader will then convert it into the corresponding sequence of function calls that you would otherwise write. So you do have that. It's just that they implemented all of that in a standard, fairly small, a few hundred lines of code library. So you don't need to have a new version of the language. You don't need to wait for a standards body to come out with with a new version of the language to get these cool new features that you heard about. And that is why you hear, well, if you talk to Lisp programmers, you will also always hear them say, that feature, we had that for a long time, or, oh, that's an interesting new feature that this cool new language has, let me do it. And they implement the feature themselves in a matter of a couple of days. And you don't have to wait for anyone else to do it. So a lot of people refer to it as the programmable programming language, or saying that it's not a programming language, it's a ball of clay that can be used to create the language that you then want to use to develop something. So finally, I want to explain one. So this is sort of moving slightly over to to another aspect of the language that. To clarify that the compilation step is not a separate step. Normally what you do, oh gosh, okay, I was actually supposed to go to a different slide first, to this one. So this is how you are programming normally, right, in C or Java. You edit your file, you compile the file, you run the program, you exit the program, and then you go back to it. Lisp is not really like that. What you do is you start your runtime, and then the runtime is running. And the runtime contains all your variable bindings, it contains all your functions. You edit the file, you compile, maybe you can interpret if you want to avoid that, but usually you compile to get all the stuff. You test your program, and then you're back here, you edit some more, you compile another function. You can compile one function at the time, test it, and then you put it together. So you're spinning here, but the runtime is still running. Now, what that means is that you can use, okay, eval when is a way to specify when something is to be compiled. Right? So you say eval when compile top level. This means that this code is executed when you compile this function. And setQ is like assignment, so I set the variable y to 10. The reason I put stars around that is it's a common practice to do that among Lisp programmers, to mark global variables. The dynamic actually, but the global variables are marked with stars around it just to make sure that you're not confusing them with local variables. And there are technical reasons why you want to do that. The compiler itself does not enforce that, but everybody does. So now, during compilation, I set the variable y to 10. And then later, when I call this function in runtime, I can actually do something with variable. It's still going to be 10. I assigned it during compilation, but the compilation phase and the runtime phase are not separate. They're both running in the same environment. So you actually have a function called compile. You can build up a function from a list in runtime. You call compile on it, it returns a function definition you use, compile optimize. That's how I implemented my a template processor for HTML that I did. Yes?
So like, how would you do an equivalent of the macro if-ed that you showed a few slides back that would just test if y equaled 10 and stick the first clause right into the code instead of reproducing an if-then?
Yes, you can do that. And actually,
because the scoping of the variables is a little...
Yes, if you want to talk about scope, okay. So compilation happens in what's called the null environment. The null environment has no lexical, active lexical scope. Right? So, since it runs in a completely different environment, if I assign a local variable, how to explain this in a fast and easy way. Okay, the very short summary is, if I run the macro expansion inside of a lexical scope, where you have lexically scoped variable, that value is only available during macro expansion. Macro expander later returns a list, but that list is just a pure list. It's not a function, so it doesn't have a closure, which means that those bindings are gone. However, there are ways around that. And I could explain that to you, but I can, okay, come to me, I'll explain later, send me an email, whatever, I'll explain in detail. But it's actually a very good question. It means that you actually understand what I'm talking about. Right, so I was going to run a small demo, but I'm actually stopped a little bit over time, actually, so I don't know.
Do it.
Right. Okay, so let's do that. This is a bit annoying. Let's quit this together. So I restart my development environment. So QL is quick Lisp. That's just a library that's used. It's sort of like apt-get in Linux, where you basically load the library, it loads all the dependencies and everything. So just load this library, which is essentially a library that I created to sort of make web service easier to deal with. So call start server like this. Now, so so let's so standard. So what happened? What I just did was to simply start a web server on port 8080, and that's this command right here. And so what I did, but it doesn't provide any pages or anything because I haven't done it. I just started the web server. So let's go to my file here and just do define handler fn, and let's call it foo and hello you. Now, so what I do here now is I just compile this one. I compile that function, no warnings, and the function is compiled. So I can compile one function at a time. All I do is I go to it, I press Ctrl+C, Ctrl+C, it's compiled. Now, it's simply, so by default, a handler function would simply just return the to the web client whatever I return from this function. Right? So now this define handler. So you might ask, okay, define handler, what is this? This looks like some kind of new syntax or whatever. Yes, it's a macro. It's a macro that I did. And now I don't expect you to fully understand everything that goes in here, but I can show you that I can go in here and say macro expand. And this will actually show me here what I would have had to type otherwise in order for this, I mean, if I didn't have macros. So what I do here is actually I assign, I don't really...
Easy, show what?
Yeah, but what I do is I just tell, during compilation, I tell the runtime that, okay, here, bind my this part of the URL to the web server. When that is called, call this function, and then I define the function, which simply just returns this text. Now, so what I wanted to do with this demo is I want to illustrate how the runtime holds all the variables, keeps all content, and I don't redeploy, I don't really compile anything. I recompile, of course, but I don't restart anything. So I use another macro that I created. So it says with parameters, and let's specify a variable name. We say, for example, bar. And now, unfortunately, I'm going to have to use one other slightly more complicated. So the format, as you remember, formatted like printf. But if I specify nil here, it means work like sprintf. So instead of printing to screen, I return the formatted string as a string. So the value was, and then so what this does is essentially takes just so here, and then I can use the question mark equals to. So what is special about this? Well, as you can see here, is I declare a variable, and the variable name is called bar. Now, how did the mapping happen from actually the string that is the parameter there, bar equals to something, and how did that map to the name of a variable, which is a symbol, obviously? Now, I mean, I could show you the macro expansion, and that turns out that it did. The macro expander did magic and figured it out, and I'm not going to go into details why. But suffice it to say, the macro did magic stuff. I did that. I could do that computation during compilation, so that the stuff I have to write is very simple. All I say is with parameters, specify the variables I want, and the rest just works. Now, so let's do something interesting. Sorry. So, okay, so what I did now was just to define the variable x as the global variable. So let's do this. So let's set x to the value of r. File. I run the hello. And now the value of the parameter x is now, it's just printed, hello. Now, it's, okay, what I'm trying to show you by doing these things is that when I type commands here, I can type any command in here. I run it just like when you go into the console of your JavaScript console in your browser, you type commands, you print the content of a variable, or you call a method or whatever. You can do that here. But this is the actual running environment. So when I was running, calling from the browser, it talked to the web server that is also running inside the same runtime. So I can do stuff like list all threads, and it would print all the threads that is running. So it's all one environment. If I decide to define a function on the command line here, I can call it ABC, and to return I don't know where it's. So now I've generated a function. I can call it like this, and I can go in the code here and say, let's just call it ABC. This is my compiled code. I recompile the file. I go here, and it gives me what is returned from the function. So as you can see, it's not. I don't simply write the code in a number of files, compile it, and then I end up with a binary that I can run and deploy into an application service. Instead, it's one running environment that is sort of growing and living. I can easily test things. I can go in. I can set the debug. I can connect, set the debugger breakpoint at any point, and change something, change a function. All while everything else is running. And in fact, they did this on one of the NASA actually used Lisp in one of the probes, and they were actually doing this, connecting to the probe itself to run these commands on the thing, on the probe that was in space somewhere, to debug and change something in real time. In pretty much exactly the same way as I did it right here, but obviously my example is significantly more simple. Yes?
How do you get a snapshot of current state?
Very good question. You can get a snapshot. There is a way of saving an image. So you can take the image, it will generate a binary that you can run or that you can load again. So you can do that. Another way, typically what I do is that after a while, I don't want to go and make too much of a mess while developing like this. So once in a while I restart the environment just to make sure that everything actually does. Because sometimes, and I can freely admit that this is probably one of the more annoying parts of doing this kind of development, is that after a while you maybe add another file, you compile it manually, move some functions around, and then when you restart your environment, it doesn't build anymore because, as it turns out, that file X needed a function, when it expanded a macro, it needed to call a function that wasn't defined because it comes in a later file, and macro expansion happens during compilation. So that's why I typically have a tendency to try to restart my environment once in a while, just to make sure, especially when I move files around. It does happen, but I mean that's the way it is. But the benefits outweigh the negatives in this case.
That way it's a binary output, right?
When you create an image, yes.
How do you get the source of what
You don't. That's a short answer. What I did here, right? Sorry. If I go in, the function I defined here, the source for that function is gone at this point. There's only the compiled version. So I can do, for example, something. Let's do something. Define foo x, y, z, and let's take two parameters x and y. Return the sum of those. So here I can call x, y, z with 10 and 20 gives me 30. So I can, as you can see, this is the function. It's compiled. So the source is no longer there. That said, depending on which environment which runtime you're using, some of them actually do save the code if you set the debug level to a certain level. But normally, if you want to keep it, you put it in the file.
So you can have interpreted list also.
That is true, of course.
Everything stays as lists in memory. I mean, disassembly is nothing else, just like creating data.
True, yeah, of course. So finally, my last slide is essentially just the links I promised. So let's go back to this one. So there are a few, so these are the major free implementations of Common Lisp. There are two other ones called Lisp works, and the other one is called Allegro. And those are commercial, and especially Allegro is ridiculously expensive. But I generally use SBCL because it's very fast. It's a very high performance compiler. Output, you know, you can make it very fast if you want to. This one is purely well, it runs in a VM, sort of like with the bytecode, which makes it easy to port. So usually this one is available on all the platforms out there. This one is called embeddable common Lisp if you need something that integrates with C. And ABCL is implemented on Java on the Java VM. So if you need something that runs in Java, and it integrates very well with Java as well, so this one's good for that. And ClojureCL is also very native compiler, also very fast, competitor to SBCL. It's a matter of taste which one to use. And finally, a few links here. I don't expect you to write them down. Anyone who's interested in this, I will make the slides available, and then you can click here. So this basically gives you instructions how to easily install it, if you want to play around with it. This is the package manager I was talking about. These guys mentioned that too. This is the one to read. This is a book from Practical Common Lisp, written a few years back, and it is extremely good. It is one of the best programming books I've ever seen in any language, because it explains things in a very easy to understand way, and also not only explains how things are done, but why, and why it's a good thing that it's done in that way. So if you are in any way interested in this stuff, go here, or just Google right now for Practical Common Lisp. You'll see the first link, and the whole book is available online. So, or you know, buy paperback. I'm sure it'll be happy about it. Yeah. So, and the RSC channel, very friendly people. Because I'm there. Anyway, yes.
I would really mention Picolis.
I think the next speaker is
Yeah.
very keen to see.
That's all what I wanted to say, because it's a newer and easier something to get into.
Let's not take that discussion right now. Suffice to say, there are differences of opinion here and there. I mean, fine. I mean, there are many different things. I'm talking specifically about Common Lisp. There are plenty of other Lisps that behave differently or whatever, have different priorities.